Okay, so the sine rule is a really useful result to with triangles, which can tell you some unknown side lengths or some unknown angles in a triangle if you've got some partial information. So basically, you've got any triangle, interior angles A, B, and C, and then opposite to angle A is side length, lowercase a, B is opposite B, C is opposite C. Whatever triangle you've got, if you label it like this formula will always hold. So sine A over A is always equal to sine B over B. This is always equal to sine C over C. And I was interested to see if some sort of similar analogous result holds for quadrilaterals. And I had a look online and I couldn't find anything. I was thinking, surely there could be some sort of result you can find, perhaps that looks like this. So sine A over A equals sine B over B equals sine C over C equals sine D over D. So let's have a look at this, see if we can find something that looks like this that will work for quadrilaterals. So let's start off, perhaps we'll just look at a rectangle as a reasonably simple example of a quadrilateral. If we label the interior angles A, B, C, and D, so immediately we sort of run into a little bit of a problem here because it's not immediately obvious which side is going to be opposite to angle A. Let's say maybe I go with this one here, then we'll say B is opposite to B over here, C is opposite to C, D is opposite to D. So let's have a look at this. Sine A over A. Well, we know that A is 90 degrees, sine of 90 degrees is just 1, so this is just equal to 1 over A. And similarly with B, angle B is also 90 degrees, so sine B over B is just equal to 1 over B. Sine of 90 degrees gives you 1. And for a general rectangle, A and B, these aren't the same length. So 1 over B is not equal to 1 over A. So it seems that immediately, just looking at a rectangle, we've kind of got stuck that sine B over B can't be equal to sine A over A. So this approach of trying to label all the interior angles and all the side lengths doesn't seem to be getting us anywhere. We seem to be getting stuck. But what if we've actually been looking at the wrong angles? So if we stick with the same side lengths, A, B, C, and D, and what if I draw in this diagonal here to actually split our quadrilateral up into two triangles? Then we've got a really nice clear, I think this should be angle A, this should be angle D. These are opposite each other within each triangle. And then you've got angle C and angle B here, similar. They're opposite to the side lengths B and C. And what's really nice about this is we can actually now apply the sine rule for triangles to get that sine A over A is equal to sine D over D. So it's starting to look a bit more like the kind of picture we're aiming for. And you get the same sort of thing, sine B over B is equal to sine C over C. So it looks like perhaps we're onto something here. So now we want to join all of this up and make sure that each of these four quantities are all equal. Well, why don't we have a look at this diagonal length, because this is common to the two triangles. If I call this L, we can apply the sine rule again. So if I call this angle here E, and I call this angle down here F, then we know that sine F over L is equal to sine A over A, sine D over D, and similarly sine E over L is equal to sine C over C, which is equal to sine B over B. So now, in order to join these up and get these two to be equal, basically what we need to have is these are equal if and only if sine of E is equal to sine of F. So this isn't going to work for every single quadrilateral, but let's have a quick look, see which quadrilaterals this does work for. So really sort of obvious solution here is if angle E is equal to angle F, and of course this is going to work, sine E is going to be equal to sine of F, which means that these will be equal, so sine A, sine D over B, sine C over C, all of these are going to be equal when angle E equals angle F. So what sort of quadrilateral have we got when E equals F? Well, you're looking at either, it could be a parallelogram, in the broadest sense, so including a rectangle, a rhombus, or a square as all special cases of parallelograms. So this is where, imagine you've got your parallelogram, this is your diagonal. These two opposite angles here are equal, and actually if you'd used the other diagonal, these two angles here would be equal too. So that's really nice for the parallelogram. But there's another case where E and F are equal, where perhaps if you imagine you've got this triangle and you flip this, you get a kite shape. So this only works if the diagonal on your kite is the line of symmetry. So imagine you take this diagonal and these two angles will be equal because you've got a line of symmetry. But if you were to take the other diagonal, then there would be nothing saying that this angle and this angle, nothing saying that they have to be equal, that their signs are equal. So this doesn't work. So you have a kite as long as the diagonal is a line of symmetry. And don't forget about convex kites as well, so this would also work for a concave kite, where these two are equal. As long as this is your line of symmetry, this would work. So we've covered some nice cases here. We've got quite a broad range of different shapes, different quadrilaterals this works for. Parallelograms, rectangles, rhombuses, and squares, but also kites, whenever E is equal to F. But there's another hidden solution here as well. Sine E equals sine F. You know that for any value of x, sine of x is equal to sine of 180 degrees minus x. So basically if E plus F is 180, so if E is 180 minus F and vice versa, F is 180 minus E, then this will also work. You'll still get sine E equals sine F. Now, what sort of quadrilateral have you got if the opposite angles sum to 180 degrees? Well, this means you've actually got a cyclic quadrilateral, or one where all four of the vertices lie on a circle. So this holds that E plus F equals 180. This applies for both pairs of opposite angles, and these sum to 180 if and only if your quadrilateral is a cyclic quadrilateral. So, for example, if we use this as our diagonal, then these two angles would sum to 180 degrees. And it doesn't matter which diagonal we use this diagonal instead, then these two angles would sum to 180 degrees. So just to conclude what we've discovered then, basically we're saying that for any parallelogram, which includes special cases, squares and rectangles, rhombi. So for any parallelogram or cyclic quadrilateral, or even for a kite, so long as the diagonal is a line of symmetry, then we'll have this sine A over A equals sine B over B equals sine C over C equals sine D over D. This is our kind of general picture. So with A, B, C and D as our lengths of the sides, and then the opposite angles formed using the diagonal. We've got C, and here we've got B. Then we conclude that sine A over A equals sine B over B equals sine C over C, which is also equal to sine D over D. And that's not bad. We've covered quite a lot of different quadrilaterals there.